Hi, I'm Reyne from the University of Sydney, and I'll be going through practice problem sample V. Now, first off the gate, let's have a look at these tests. And what we can see by looking at these tests is that we don't have any unsaturation present, we don't have any oxidation occurring, and there is no carboxylic acid present. Okay, they're all negative tests, which is great. It narrows down our options considerably. Now, as I've done previously, I like to avoid looking at IR and mass spec until after I look at the other data, and I come back to this to try and confirm some of what I'm starting to suspect. Now, if I come down to the carbon NMR, so the carbon NMR, I can see a total of 4 peaks. So let's label these 1, 2, 3, and 4. We can chat about them a bit. Now, what we can see here, first of all, is that they're all the same height. Now, this doesn't mean that there are only 4 carbons. It could mean that there are 4, 8, 12, 16, but it tells us that the ratio of these carbon environments, they're all similar to one another. And what we now need to focus on is the positioning of these peaks, so what their chemical shift is. We can see that, for instance, peak number 1 is the most left, the most downshifted, sitting at about, I don't know, 42, about just under 42 ppm. And then as we go from 1 to 4, we gradually move closer and closer to 0 ppm. Now, this typically is associated with proximity to a electronegative species. So if we were looking at something that had, say, a carboxylic acid, we would expect to see a carbon environment way down at about 180 ppm. It's very de-shielded. So something at about 40 tells me that there's something that's de-shielding it, but not heaps. So we're going to be on the lookout for something that could be de-shielding these carbons, but not substantially. Not too much more to pick out from that right just now. Now, the proton NMR, this is a bit of a trickier one. When we look at this proton NMR, we can see that we've got, at a first glance, it looks like 2 nice triplets, one at about 2.6 and then one at about 1.9. And then we've got a whole big mess at about 1.5. So I'm actually going to, first of all, label this peak at about 2.6 as A. And then I'm going to stop and look at this table of peak data immediately beneath, because the table here tells us what peaks have been identified here, and it actually breaks apart that mess and tells us a bit more about it. And what it's saying is that we've actually got 3 peaks really close to one another, overlapping, and this is hard to pull apart. But I'm going to now label these as, well, there's our A for 2.68, but we'll call this one at B, 1.5, C, 1.43, D, 1.33, and then E, for 0.92. So I can also label E up here, but realistically, B, C, and D, they're all kind of stuck up in that little mess in the middle there. And we'll come back to that. But what we want to try and pull out of here is a bit more information about the peak area ratio as well as the number of peaks. Now, first of all, the peak area ratio tells us how many protons are in each of those environments relative to one another. So we can kind of see that we've got a 2, a 2, a 2, 2, and a 3. Now that's kind of interesting because the 3, right, is normally what we would see if we've got, say, a terminal carbon. But the fact that we only have 1 3, I mean, what does that mean? It means that maybe we have a mirrored structure. Maybe that terminal carbon, there are 2 of them and they just happen to be the same. Or perhaps we have something present that is not a carbon and is terminal in our structure. So that's something to start thinking about. When we also then look at the number of peaks, the number of peaks is then telling us a bit about, well, what is adjacent to our proton environment. And when we look at these, we can kind of see, you know, a 6, a 3, a 3, and a 5. And then we see a 1. Now, a 1 is a bit of a curveball. When we think about a 1, a singlet, in the other examples I've gone through that you may or may not have seen, that's often really what we see when we see an alcohol. And the reason that we see in alcohol is that the alcohol proton doesn't interact with the proton environments and carbons. It just doesn't split with them. Now, we've already established that there's no alcohol present. So we need to think, well, what other kinds of species may have protons on them that are similar to an alcohol? And my first thought is maybe there's an amine. We haven't tested for the presence of an amine. The singlet here is kind of telling us a little bit about maybe there is those amine protons and they're not interacting with the carbon protons. And also, we've already talked about how in the carbon NMR, there's something that is more electronegative than carbon that's de-shielding the carbon next to it. And we know that nitrogen is not as electronegative as an oxygen. So these things are kind of coming together, but we need to confirm this. So let's kind of maybe move back up here to our mass spec and our IR. And I think in a rare change of circumstance, I might look at the IR first. Normally I go to the mass spec, but I'm not sure of what functional groups are present. So I think I need to look at the IR to try and narrow that down. Now I have here my peak at about 3000. As usual, that's going to be our carbon hydrogen stretch. I can see my peak here at about the 1450 sort of area. It's going to be my carbon hydrogen bend. And then if I was, for instance, looking for, say, a ketone or a carbonyl of some kind, I'd expect a 1700 peak. There's none. If I was looking for an alcohol, I'd see a really broad peak up at about the 3300 sort of area. There's none. But I do see, however, a peak here that's at about the 3400 mark. That's not so broad. And this is where you would need to go back and consult your table that's in this document. And we need to start thinking, well, what other options are there where we see peaks at about that signal? And the one that we do see is going to be the nitrogen one. Okay, so a nitrogen to a hydrogen, we tend to see it about 3300 to 3500. And this is great to see. This then confirms for us our suspicions around there being something that was electronegative. It's got the protons that won't interact with our carbon proton environments. It's also got a bit of electronegativity, so it's going to de-shield some of our carbons. So let's then look at our mass spec. As I've done before, I'm going to assume that I have the simplest ratio of carbons and hydrogens as per the carbon and proton NMR. So let's say that we've got 4 carbons, which would give us 48. If we come down here to our protons, if we count the number of peak area ratio numbers, we've got 2, 4, 6, 8, 11. So 11 protons, which will give us 11 towards that count. And then we have the nitrogen. All right, so we're saying that there's a nitrogen here based on the IR data and our suspicions from the proton and carbon. And if we think about that, a nitrogen is going to account for about 14, don't know what I'm saying, about 14. And if we sum all of these together, we're going to end up with 73, which is great. Once again, this is the pieces are coming together. So this kind of confirms for us that our assumption that there is a nitrogen is feasible. So let's then have a bit more of a think about how we can propose a structure. Now, what we've seen in this carbon NMR is that the peak 1 must be closest to the nitrogen. It is the most de-shielded, but then we see effectively a stepwise movement back towards 0. So peak 2 is about 35, peak 3 is about 20, peak 4 is just under 15. And that suggests to me that maybe we have a straight chain of carbons away from that nitrogen, because the electro withdrawing effects of the de-shielding of that carbon doesn't just stop there. It can flow on to subsequent carbons, but to a lesser extent. It would also explain some of the information we see in the proton NMR, how the triplet at peak A is quite de-shielded, whereas the triplet at peak E is not very de-shielded at all. And then we have a bit of a mess in the middle where there are similar things. So let's run with that. Let's say we're assuming that there's going to be a straight chain, and we'll talk a bit more through that. So let's say that we've got our 4 carbons, and then we have our amine off of the end there. I'll draw that properly. So we got a hydrogen and a hydrogen. Okay. Based off of this, can we map some of our carbon and NMR data to it? Now, our carbon NMR, well, we're saying that peak 1 has to be closest to our nitrogen. The nitrogen is going to pull electron density away from it, therefore shielding it. So 1. And then if we follow that idea that as we get further away, the effect of the nitrogen reduces. So that would be 2, 3, all the way to our terminal carbon, which would be 4. Now that makes sense for our carbon, but does it make sense for our proton? Now let's start with perhaps the 2 triplets. The 2 triplets are maybe the easiest to work with. So if we think about what a triplet means, it must mean that there are only 2 protons in the neighboring proton environments. If we think about carbon environment 4, our terminal carbon, now change color to blue, okay? That one will only have the protons on carbon environment 3 present, which will be 2 of them. So that would be a triplet, and it's going to be the least de-shielded. So we would expect this to likely be E, okay? And then we need to think about, well, what could the other triplet be? It's the most de-shielded. It's going the furthest to the left. So maybe it is carbon 1, but it's got the nitrogen next to it with 2 hydrogens, and it's got carbon 2 with 2 hydrogens next to it. But we have to remember that the nitrogen hydrogens won't interact. They don't split. So really, from the perspective of the proton environment at carbon 1, it's only concerned with the hydrogens at carbon 2, therefore a triplet. The N+1 rule, 2 hydrogens must be a triplet for a peak. So this would then be A. We're left with B, C, and D. Now we can rule out B very quickly. As we talked about with oxygens before, if you've seen some of the other examples, they tend to have a singlet because they don't interact. So the proton and an oxygen on an alcohol, for instance, will be a singlet, and it's similar for an amine. So we'd expect that B will correspond with that nitrogen and the 2 protons that are on there. And that matches the peak area ratio as well. 2 protons that are there, but we see it in a singlet because it doesn't interact with anything around it. We're then left with the signal C 1.43 that has 5 peaks, and the signal 1.33, which has 6 peaks. And if we then think about counting the number of protons in the neighboring environments, at carbon 2, we'd have 2 protons at carbon 1, 2 protons at carbon 3. We would expect to see 5 peaks. So therefore, this would be C. And we can confirm then that D will be at carbon 3 because it has 3 protons at the terminal carbon, and it has 2 protons at carbon 2, 5 protons in neighboring environments. So we see 6 peaks at that signal. Everything lines up. So the last thing to do is then to name it. And this one we would name butane, and it's at the first amine. So butane 1 amine. So it's telling us that there is an amine at the first carbon of a butane chain. And that's it. Cheers.